Okay, so what exactly is electric flux? Okay, so before you learn about electric flux, you need to have knowledge regarding electric field. So we know saying that electric field is given by what? Ke, which is a constant, times Q over R squared. So Q is a charge, R squared is, of course, it's just the distance between the charge and the point. Okay, so now the electric flux, which is given by this symbol here, is given by the formula E A. What exactly is the electric flux? So we are talking about electric fields. So for this topic here to be easy, just think of it as magnetic, think of it in terms of magnets. Okay, we've got the North Pole and the South Pole. So with magnets, they've got fields. Okay, so these are field lines. So just think of it as such. So the same way we've got magnetic fields, we actually have what? Electric fields. So these electric fields also have lines. Okay, now these fields, when they pass through a specific area, then that right there is your electric what? Flux. So say this here is a triangle. Okay, then you've got these field lines that are penetrating through, so not a triangle, a rectangle, penetrating through. Okay, they are coming out from this other end. Then the electric flux here is given by E, which is the electric field, which is this now, the electric field, just as it is with a magnetic field. This is here is a magnetic field. When you add a metal here, it won't get attracted. When you add it here, it won't get attracted, but as long as it is within the field lines, it will get attracted. In like manner, these are electric fields. So if this here is your area, then the electric field flux will be the electric field times the area of the rectangle. If it's a circle, okay, then it will be given by showing the circle a sphere. Okay, then somehow you have the electric fields penetrating, they're coming from the inside, then they're like going on the outside. Then the electric field will be given by what? Sorry, the electric flux will be given by E A, where A is the area of a sphere. Now we need to understand saying that with electric field, it is Ke, as I stated, Q over R squared, where you've got a point and then you've got a charge. Then this is another point, this is a charge. The orientation of the electric fields would depend on the charge. So if this is a positive charge, the orientation of the electric field will be directed away from the positive charge. So that is why the electric field has got this symbol here at the top to indicate what? The magnitude. But if you have a point in space, then this here is a negative charge. Then the orientation of the field lines will be directed towards the negative charge. Hope we got that right. So yeah, the electric flux again is equals to EA. Okay, now imagine we're talking about a closed surface. Okay, this here is a surface, it's closed completely. Then you've got a charge inside. Okay, and we know saying that the electric field has got everything to do with one charge. Okay, and R is the distance from the charge to the point in space where there is that electric field. So this here is a closed surface, as we may see. Now assume, of course my drawing is not perfect, but assume this here is a sphere. Okay, for any closed surface, the electric flux is given by the following formula. Okay, the electric flux is given by Q over epsilon naught, where this here is a constant. It is given by 8.85 times 10 to the power negative 12. Okay, it's a constant. The same way we know saying that Ke, which is found here, is given by what? 8.99 times 10 to the power positive what? Positive 9. So it is important for us, we know saying that the electric flux is given by EA. For a closed surface, talk about a sphere in this case, let us use the formula for a sphere. So it is going to be, the electric flux is given by what? E for the electric field. Then the area of a sphere is given by what? 4 pi r squared. And then we know what E is. E is the electric field, which is given by which formula? This one right here. So let's write E in that formula in terms of this. So it's going to be, KEQ divided by what? R squared. This is E, and this is 4 pi r squared. So what we can do now is cancel this out. Okay, what are we going to remain with? KEQ times 4 pi. Now, take note of this, yeah? You have, for now, let me just create a circle here, sorry, square. So, you have KE, we know what KE is. It is 8.99 times 10 to the power positive 9, that's a constant, yeah? Now, this KE, it is equal to 1 over 4 pi epsilon naught, which is here, 8.85 times 10 to the power negative 12. Because remember, the electric flux of any closed surface, it doesn't matter whether it's a sphere, whatever it is given by the charge divided by the absolute node, where this is a constant, which is 8.85 times 10 to the power negative 12. How did they come up with this formula? That's what we're doing right now. Okay, so you have, let's start from here, electric flux, and then you got EA. A is the area of the sphere, 4 pi r squared. Okay, r cancelled out, then we reach here. So KE is equal to 1 over 4 pi epsilon naught. Now, if you substitute this value of 8.85 times 10 to the power negative 12 in here, and then you solve for KE, okay, you say 1 over 4 pi times 8.85 times 10 to the power negative 12, you'll find that KE surely is equals to what? 9.8.99 times 10 to the power positive 9. You can just try it out yourselves. I'm trying to work under time. So now, getting this expression of KE and substituting it here, we shall have our final answer. So now, let me just do this. So we have KE is equals to 1 over what? 4 pi 4 pi what? Epsilon naught. Okay, and the same goes for this here. Yeah, actually, yeah, that's the case. Okay, so we know, saying that what we ended with was what? Let's see, what did we end with? We ended with KEQ 4 pi on the outside. So that's KEQ and then what? 4 pi on the outside. So let's replace where there's KE, let's add this. So where there's KE, let's add this expression. So it's going to be, the electric flux is equals to 1 over 4 pi epsilon naught, which is this right here. Then you've got 4, sorry, this is for this here is this here is this. So this will be Q times 4 pi. So let's just multiply this together. So the electric flux will be equal to Q 4 pi divided by what? 4 pi epsilon naught. So let's cancel, as we may see, we can actually cancel out the 4 pi and the 4 pi. So this will go, that will go, and finally we have our answer, which is what? Q divided by epsilon naught. So for any closed surface, whether it's a triangle, whether it's a circle, whether, sorry, whatever it is, as long as it's a closed surface, and then you've got a charge inside, the electric flux is given by this formula. Now I had to explain this so that we understand where it is coming from, because the more, when we understand, it tends to be easy for us to solve for. Sometimes you take the electric flux as EA, then maybe they ask you to find the value of I don't know, maybe let's see, what value can they ask you to find the value of r, the distance. Okay, you might want to do this first, then you get to this. Instead of you going on and on, you can actually stop here and then solve for r. Sometimes they ask you to find, no, maybe find the value of the charge, but you talked about the electric flux. How can you relate the two? Convert this electric field to this formula, and then you pick it up from there. Just ensure that you understand where formulas are coming from. So since we said it is for any closed surface, yeah, let's do this. This, we said, doesn't matter whatever it is, as long as you've got a charge, the electric flux is given by what? E, the electric field, times the area. Remember, the electric flux is just that amount of the electric field that has passed through a specific what area. So if you have a charge inside, then that electric flux, because remember, that electric flux will be the area times the area, times let's see, the area times the electric field. So because there's a charge inside, there's a charge, so the electric field lines will definitely have to pass through in that manner. So they'll pass through that what thing that you have right there, that area, because that's what the electric flux is. Now imagine you've got a triangle. Okay, this is what you have, and then electric field lines pass through like so. Now, how are we going to find the electric flux for this? As you may see, as long as it's not touching the ground, this ground do not have an electric flux because it doesn't cover this area. It does cover this area, and so does it cover which area? This one. So as you may see, this here, there's an angle here. Think of this as a tent or something. I want it to be, yeah, there's an opening here. So this here is the angle at which this has opened. Okay? So now, using trigonometry, you know, saying there's what we call SOHCAHTOA. So this here is the opposite, that's sine for so, opposite and hypotenuse, but our interest is not in the opposite, because that's the ground right there. So how about we look at the adjacent and the hypotenuse. So the electric flux for an area that has been somewhat tilted is given by, electric flux is given by what? E A cos theta. This is the formula that we're supposed to use for those which have been tilted, of course, where EA is the main electric flux passing through the hypotenuse. Then for the adjacent, then you may have found the electric flux specifically for this right here, because that's the adjacent, that's your X value. If that wasn't enough, let me just try writing it in this form. So this here is your X, sorry, this is, yeah, let me take that as our X. Then this here is, since the theta is here, the angle is here, so this would be so as an opposite, then this is the hypotenuse, then this is the adjacent, then this is the hypotenuse, because remember, we don't follow this specifically the number line here, no, we follow the angle. So opposite, adjacent, hypotenuse. So for X, that's what I meant to say, is equals to the hypotenuse cos the adjacent. How did we come up with this? We used k for adjacent and hypotenuse. Adjacent, hypotenuse. Then this is cos theta is equals to the adjacent, which is x, over the hypotenuse, which is this. Then we said over 1, we cross multiplied, we had x is equals to what? H cos theta, which is this. So I think I've said enough about this. Let me just have us do some examples from college physics. Remember, as long as you got an enclosed charge, your electric flux is an enclosed charge, yeah, your electric flux is given by what? Q, where the charge is the charge that is inside, divided by what? This value, which is 8.85. It's a constant. So let's do this simple exercise, yeah? In fact, I'm working under time, so let me try to be quick. So this here is a closed surface, yeah? And then you've got a charge inside. Let's call this a -2, okay? What is our electric flux? So as earlier discussed, for any enclosed surface, the electric flux is given by what? Q, where Q is a charge inside, divided by epsilon naught. So the electric flux here is going to be -2 divided by 8.85 times 10 power negative what? -12. That is your answer. Of course, you can do this and divide it. So that's for diagram A. Let's go to diagram B. Okay, don't focus on these two. Everything else will get to these. So what is the electric flux here? Okay, so the electric flux, again, for any enclosed surface, is given by Q divided by E, which is the absolute node. Q is a charge inside. Q is a charge inside. So, as we may see, how many charges do we have? We've got 2. That's 2 plus 2, rather positive 2, and -2. So we'll say positive 2 plus -12, rather. That's -12. So divided by epsilon naught. So if we just do the math here, this will be 2 positive times negative. It's going to be a negative -12 epsilon naught. So here, what are we going to have? -10 divided by epsilon naught. So this is your electric flux. You just have to do the math. Then, where of course this is a constant. So we're going to move on to this. So what is the electric flux here? Okay. Yeah, I wanted to say you can pause the video, but please I think you can just try this out. So that would be 5 plus -2 plus -8. Okay. Then you say divided by what? 8.85 times 10 to the power negative what? -12. Then you do the same. Now, as you may see here, there's no charge inside. What is the electric flux? The electric flux here is equal to what? 0. Because anything 0 divided by anything is just 0. So there's no charge, there's no electric flux when there's no charge inside. So with that being said, let us just move on to example under the electric flux, example 15.7 of page 517 in college physics, okay, survey, the 11th edition. So you find these, okay, you would have diagram A, you have diagram B, and then you have diagram what? Diagram C. This is what you're going to have. Now, this which is dotted is a Gaussian surface. So these are Gaussian what? Surfaces. So for any enclosed surface, and then it has a charge inside, excuse me, the electric flux is given by the formula, of course, Q over E. So this here is a Gaussian surface, not this. This is. And so is this. This which is dotted. Okay? So they're telling us, saying a spherical conducting shell of inner radius A and outer radius B. So inner radius, it's the same thing, but they are just changing the Gaussian surface to see what you're going to find for your electric what? Flux. So find the electric. So we've been taught saying that, okay, the inner radius A and outer radius B carries a total charge plus Q. Okay, so the inner radius A and the outer radius, they carry a total charge which is positive, which is now this. That's what they're telling us. Yeah. Then they're saying, okay, find the electric what field in the interior of the conducting shell for R is less than A. Okay, find the electric field in the interior of the conducting shell for R is less than A. Now when we look, when R is less than A, okay, that's for figure 20. They've even specified figure 15.29A. So that's for this whole figure, but for A specifically. They said for R is less than A. So in other words, the radius has to be less than A. But when we look, starting from here, okay, this is a circle. Then this is the radius of the circle. Well, of course, this isn't perfect, but this is the radius of a circle. Now they're asking for the interior, okay? In here, this here, from here to here, that is A, meaning less than A, meaning wherever from starting from here coming down, we don't have a single Gaussian surface. Okay, find the electric field in the interior of this. So we don't have it's not necessarily a Gaussian surface, but what they're asking for is the electric what field. But remember, the electric field has everything to do with the what, the charge. It is Ke over R squared. But there's no charge inside, is there? No, there's no charge. So the electric field there is what? Is 0. I don't know if you get that, but please, if you didn't, you can just replay the video. The electric field is 0. There's no charge inside because the electric field has everything to do with the charge. Number 1. Number 2, and the field, yeah, so number 2, B rather, they're saying the electric field outside the shell for R is greater than what? B. Now, note, they're not looking for the electric flux, but they're looking for the electric field. Okay? So electric field, yeah, so for B, they're telling us, okay, find the they're saying the electric field, find the electric field, of course, outside the shell for R is greater than what? Greater than B. Notice, they said for R is greater than what? Greater than B. So where the radius is not B, but greater than what? Greater than B. So what we're going to have is the following. We're going to use this diagram. I forgot to do this. This here is an R. Okay, so the R, this is B from here to the outer surface, that's B. From here to the inner surface, that's A. And remember, it is about having the enclosed surface. Then you're going to say the electric flux with a charge, of course, a charge or 2, it doesn't matter, is equals to a charge inside divided by epsilon naught. So this is the enclosed surface. And as we may see, this here is a what? A positive charge. So this here is for R is greater than B. This is B, B ends here. But R goes and exceeds here. So we are reaching the Gaussian surface. And as you may see, this whole thing is charged. It doesn't matter whether this charge comes in form of a circle, in form of a triangle, as long as you've got a charge inside, then you can actually apply what? This formula. So this whole thing, the spherical conducting shell, is made of a positive charge. So the electric field, which is what they're asking us to find, will be, you do this, the electric flux is given by what? E A. Okay, and we know saying that the electric flux for any enclosed surface is given by this Q over epsilon naught, where Q is a charge. So you just leave the Q as it is. Okay, then you solve for E, which is the electric field they're looking for. Then we have our answer. But I want you to take note of this here. Is this some other, of course, it looks like some other surface, but this here is a what? A sphere. Of course, it is a sphere when you look at the book. So meaning the formula, it is necessary for you to actually substitute the area of a sphere. So therefore, E is given by Q as for the charge inside, but it is important to write it down as big Q just to avoid my inconveniences. So this Q, that is for the charge inside, is equals to 4 where there's area. Let's put area of a sphere, because at least we know the shape of this thing. It is not an irregular shape as it was with these. So it's going to be 4 pi r squared times epsilon naught. This is your electric field. Then moving on to C, they're telling us, okay, saying if an additional charge of negative 2q is placed at the center, find the electric field for R is greater than B. So this here is for R is less than, this here is less than, this here is A, this here is B, this here is R. So this is R is less than A and B. And as you may see, there's no charge inside this Gaussian surface. The charge is where is outside. But in this case, the Gaussian surface is outside and then the charge is inside. This charge can come in the form of a square, like I said, a rectangle, it doesn't really matter as long as you have the charge inside. Then you can find inside the Gaussian surface. Then you can find the electric flux. In this case, this here is the Gaussian surface, but it is smaller than the charge, then the charge is actually outside. So the electric flux here is what? 0. So moving downwards up, on C, what did they ask us to find? They've said if an additional charge, so if they've added another charge and they specified saying for which diagram, for R is greater than what? B. This R here, as you may see, this R is smaller than B. This here is B, this here is A, this here is R. This R is smaller than B. There isn't any R here. This is for R is greater than B. So they've added another charge. And this charge is what? Negative 2. So this charge here is negative what? Negative 2 as our charge. So what we're going to do is this. So this negative 2 charge has been placed inside. Now remember what we did here with this. We said if this is negative 2, the electric flux will be given by what? The charge over epsilon naught, where this negative, okay, will only come at the top. Then this here is 8.99, so where 8.87 times 10 to the negative 12, okay. So when you have two different charges, you add them up. So as you may see, this here is a positive charge, okay, inside a Gaussian surface. Then they've added another negative charge, so it will be the positive charge plus the negative charge, which is 2q. So it's going to be q minus 2q, which is equals to what? Negative q. Thus, your electric field will be, this is how you're going to find the electric field. You say the electric flux is given by Ea, okay, which is equal to the charge divided by what? Epsilon naught. But in this case, the charge is what? Negative q, because of the math that was going on, because of this additional charge. So you're going to say negative q over E, then you say divided by what? A divided by, divided by A divided by A. We do that, we'll have E is equals to negative q divided by A epsilon naught. You have your answer. And like I said, at least we know what this is. It's a sphere. So we're going to use the area of a sphere. So this would be negative q divided by what? 4 pi r squared epsilon naught. This is your answer. And then for C, so rather for D, they're telling us, hold on. And then lastly for D, they're telling us, okay, find the charge distribution on the sphere for part C. So we want to find the charge distribution on the what? the sphere. So it's all about the sphere itself. Remember, from here to here, that's our, is that our B? Let's see. No, that's our A. So this here is your A, this here is your B. You want to find the charge distribution here. Okay. First, we need to find the charge distribution of the interior surface. Then we find the charge distribution on the exterior, which is B, on the outer part of this surface. Okay. So we say EA is equals to excuse me, the charge inside, that's the formula as we know it, divided by the absolute node. Okay. Now the charge inside, we want to start with the sphere inside first. We say for the charge inside, that would be the charge at the center. Okay, which has the center, of course, which is to say the additional charge which you had to put in here of -2. Remember? Yeah. So this, it will be the charge of this at the center plus the charge of the interior surface. So that would be the charge here and the charge here, because we want to try to find the charge distribution of this thing. So divided by epsilon node. Okay. Now our interest is in this, the charges. So this, we equate it to 0. So it will be the charge at the center plus the charge of the interior surface should be equal to 0. Then we know that the interior surface is this, and what they're asking us to find is the what? Charge distribution on the surface. So let's make this the subject of the formula. So we take this to the other side, rather we subtract both sides by this. We're going to have the charge interior, which is this here, the interior of the surface, which is what they're looking for, of course, should be equal to the negative, okay, charge of the center. Now we know what the center was. The charge at the center, that additional was -2, and besides, they specified in the question saying for C, -C. So for part C, of which we were solving this question, this sphere specifically, not the other two here. We were solving for this here, not these two. Why? They said for R is greater than B. So should be equal to this. Okay, that is what we're trying to find, the charge surface. So this would be Q is equals to, what is our this is negative, and what was the charge? It was -2Q. That was the additional charge. So this will be negative times negative, which gives us a positive. So it will be positive 2Q. Then this is the charge surface where, for this, the interior. Okay. Then what about for the exterior? Okay, or for the outer surface? That's going to be the charge on the outer surface. Okay, let me just say OS for outer surface, plus, okay, the charge on the inner surface. This should be equal to the total charge. Okay, now we now make, of course, Q outer surface as the subject of the formula. Okay, and what is it that we're going to have? So it will be the charge on the outer surface should be equal to negative what? The charge of the inner surface. Okay, plus inner surface, plus it goes this side. Rather, we subtract both sides, of course, we know that, but yeah, for the sake of making things simple. So Q. Okay, now think of it as infinity minus 1. It's still equal to infinity. Of course, you'll come to understand this in mathematics, engineering mathematics. That is to say, if you like to start doing engineering. So this outer surface, charge for the outer surface will be the charge of the inner surface minus the actual charge, which will just give us the charge, negative for that matter. So this is your final answer. Now, I'm going to be doing what's this engineering lessons, that is to say at Molongosh University, but it doesn't matter. Well, by that I mean to say you are going to be having free lessons online during the holiday. So kindly subscribe to the channel. This is how the lessons will be conducted, of course. And yeah, please, you can share this to your friends if you'd like them to pass, of course. Yeah, and please, the emphasis is on subscribing. Yeah, it's for free.